How's everybody doing this morning?
How are you?
I'm doing good. Doing really good. Did anybody remember to wake Green Day up today? Does anybody get the reference? Green Day does a song, Wake Me Up When September Ends. So it's October 1st. A lame joke to add on top of all my other lame jokes. Well, I know that people are still trickling in, but the clock just turned to 9, so I'm going to get started. So, as is tradition, here is our participation question. I think you can kind of tell what we're going to be talking about today. The reason for the seasons. At least the scientific reason for the seasons. And so I always like to begin by kind of getting a baseline understanding of where people are at with the concept of seasons. So for today's warm-up question, why do you think we have seasons? And if you know why, you can put that down too. Why do you think we have seasons? So take a few moments, write down your thoughts. I will, as usual, paste this link a few more times as people come in. I see a few more people coming in now, so, and then we will get started. Move this over here. Oops. For those who just came in, I will post the link again. More people are coming in now. All right, let's take another 2 minutes. For those of you who just came in, I'll post the link again. For those of you who've been here, I'm sorry I'm blowing up your chat box with the link, but just want to make sure everybody gets it. And just as I did that, I think 2 more people came in. Okay. Okay. Got a few more people who still need to respond. So I'll paste this link one more time for those of you who just came in, and then take one more minute and then we will go into it. Alrighty. There it is. All right, I think a few people still need to respond, but let's take a look and see what the general consensus was, what people were thinking. So let's see here. We have seasons due to the tilt of the axis and the circling of the Earth around the sun. These two factors allow each hemisphere to be tilted towards the sun and opposite sides of circling around the sun. So maybe it has to do with the tilt and then our orbit around the sun. Okay. I think we have seasons to aid the course of nature. So this one's a little bit more existential, a little bit more of a sentient planet. Let me post that link one more time. So we have it to aid in the course of nature. I assume it may be due to Earth's rotation around the sun. The Earth rotates on its axis. We have different seasons based on the position of the Earth and relative to the sun. For example, when the Earth rotates closer to the sun, that is when our spring and summer occurs. Somebody's Eurocentric. I'm guilty of that too. We live in the northern hemisphere, and so, but remember, the seasons are flipped in the southern hemisphere. We have seasons due to the Earth's orbit around the sun, each of which is distinct in its angle and is hit by sunlight. The way we orbit around the sun, the tilt of Earth's axis is tilted, the tilting of the Earth while rotating around the sun. Another existential answer, there are things that need to happen at different times of the year. It helped humans to define the times. The Earth spins on its axis that produces night and day. The Earth's axis is tilted due to its orbital plane, which causes the seasons. Earth moves its position around the sun as it moves, as the climate changes, due to its orbital position. We have seasons because the Earth is tilted on its axis. Due to the position of Earth in relation to the sun during different times of the year. As the Earth orbits around the sun, it gets closer and further from the sun, which creates different seasons. So that's a common answer I'm seeing. So I'm seeing a lot about tilt. I'm seeing a lot about distance from the sun. And then I'm seeing some existential answers as well. Okay, rotation around the sun, different angles. Axis is tilted, something to do with orbit, due to weather changes throughout the year. Earth's rotation, to create balance in the planet, another existential answer. The way the Earth tilts. Okay, well, good. So a lot of good thoughts there, a lot of good answers there, and there's a little bit of truth to some of them. The one bad news is that Earth is not a sentient being. Like, the Earth itself is not a sentient being. So it doesn't intentionally make seasons happen. That ends up being just what happens. It's just a natural occurrence. That being said, let's talk about seasons, because when talking about climate change, one of the things that we're really concerned about is how it affects our seasonal cycles. Now, there's some things that we can't change, and there's some things that we will never be able to change because they're greater than us. Earth's orbit around the sun, Earth's tilt, the rotation of the Earth, those are things that humans don't do anything with. But as additional greenhouse gases are added to our atmosphere, as we have changed our land surface, that has definitely changed the intensity of the seasons and what happens during those seasons. So that being said, let's talk about seasons. So, here we go. So what we're going to do today is we're going to talk first off about the angle of incoming sunlight and how that affects a location's temperature. Then we're going to talk about this thing called latitude, which is simply the distance from the equator, and how that actually affects the amount of sunlight we receive. We're also going to talk about how the distance from the sun changes throughout the year. And you would actually be surprised when we're closest to the sun and when we're farthest from the sun. And then at the end, we're going to talk about what are called climate zones and how the tilt of Earth's orbit influences those climate zones. All right, so let's do that. So, the first thing. So there are 7 key facts I'm going to present today. The first fact is that the higher the sun is in the sky, the more heat you're getting. So when the sun is highest in the sky, incoming sunlight is most intense. And I'll actually show you how that works in a few moments. So the concept here is what is called the angle of insolation. Insolation is just one of the cutesy abbreviations that we in the wonderful world of weather do. In stands for incoming. Sol stands for solar. And ation stands for radiation. I guess they use the ation instead of the rad, otherwise it'd be insolrad, and that doesn't fly off the tongue as easily as insolation. So insolation just means incoming solar radiation. And the angle at which sunlight enters the Earth or reaches the surface of the Earth is actually really crucial to how intense the sunlight is. Let me demonstrate that for a second. So I just turned off my little light over here. I'm going to unplug my drawing pad. So I have this drawing pad right here. If I move it too far away from myself, it sort of blends into the background, but here we go. And right here, I have a flashlight. This represents the sun. So when the sun is directly overhead, what you end up seeing is a small but very, very bright circle. What that means is that the sunlight that's coming in is concentrated over a small area. Because it's concentrated over a small area, it's much, much more intense. However, watch what happens as I lower the sun on the horizon. Look what happens to that beam. So, sun overhead, sun overhead, sun much lower on the horizon. What happens is that beam actually does 2 things. It stretches, so it covers a larger area, but in that process, because you have the same amount of solar radiation now covering a larger area, it's more dilute. And as a result, it's not as intense. So when we have the sun directly overhead, the energy that we get from the sun is very intense. This is also why it's warmest in the afternoon or a little bit after noon itself. It's because at noon is when the sun is the highest in the sky. That's when we get the most sunlight that we get. There's a little balancing act between what comes in and what goes out that actually really influences when the warmest time of day is. That's beyond the scope of this class. But when the sun is highest in the sky, incoming sunlight is most intense. However, as the sun dips on the horizon, that same amount of sunlight spreads over a larger area and is therefore less intense. So that's the first thing that really, really matters with seasons, because the angle at which we receive sunlight actually changes throughout the seasons. During the summertime, the sun is higher in the sky, therefore the sunlight we get is more intense, therefore it's warmer. On the other hand, in the wintertime, the sun is lower on the horizon, therefore it's more diluted, it's more spread out, and therefore we don't get as much sunlight, it's not as intense, and therefore we're cooler in the wintertime. Now, that's not the only thing that changes, but that's one of the important things that changes. So this is just basically, this is just basically what I just did with my little writing pad and this flashlight, just drawn on a textbook style image. The same thing, when the sun is high in the sky, the beam you get is much smaller and it's much brighter. But when it's low on the horizon, it's much more spread out and it's much dimmer. So one more time, when the sun is highest in the sky, that beam of sunlight is very concentrated. When the sun is low on the horizon, that beam is very spread out. Okay, so the second thing, the angle at which sunlight actually hits us is highly dependent on latitude. So I have briefly talked about latitude in this class before, but not really in any honorable way, in any way that actually does it justice. So now I'm going to talk about latitude. So before I show you the text on the slide, let me actually show you how latitude works. So here is our big, round, not red Earth. So there's our Earth. Up here is our North Pole, where polar bears are drinking Coca-Cola with Santa. Down here is our South Pole, where the penguins from Madagascar are dancing with happy feet, and other references that show you that I don't watch many of those movies. And halfway in between the North Pole and the South Pole, where the Earth is, I'm going to use this word, fattest, that is the equator. So that is the equator. At the equator, the latitude is 0. At the equator, the latitude is 0. Now, as you move away from the equator, your latitude increases. Increasing latitude. On the northern side, we say that the latitude is north of the equator, but the same is true on the southern side as well. The further away you get from the equator, the more latitude increases. Increasing latitude. And in this case, it's south of the equator. So the concept behind latitude is the distance from the equator. Now, one of the reasons why the distance is given in degrees is it has to do with the angle between the center of the Earth and wherever you are at. Latitude equals angle degrees, and the angle down here is in degrees. That being said, I don't really care if you know that part. I just wanted to explain that's why we give it a number in degrees. But latitude is the distance in degrees from the equator. Latitude is distance in degrees from the equator. Okay. I think I can just clear this. Let me click on. I guess I can't. Oh, there we go. Perfect. So, latitude is simply the distance in degrees from the equator. If you're on the equator, the latitude is 0. And the further away you get from the equator, the greater the latitude becomes. Once you reach the North Pole, it's 90 degrees north. Once you reach the South Pole, it's 90 degrees south. So that is how latitude works. When you're on the equator, the sun is high in the sky year-round, almost always directly overhead. It varies a little bit to the north in the summertime, a little bit to the south in our wintertime. But in essence, if you live near the equator, the sun is almost always overhead. As a result, it's pretty hot near the equator. The other thing that's very interesting about the equator is not only is it hot there, but it's consistent. The temperature near the equator really doesn't change from season to season. The temperature almost stays the exact same year-round near the equator. Now, on the other hand, as you move towards the poles, the sunlight is really, the sun, if it's out even, is low on the horizon. And as a result, regions of the poles get very little heat. The other interesting thing that happens at the poles is that the time that the sun is out also varies greatly. If you live near the equator, you get 12 hours of daylight and 12 hours of darkness every day. However, if you were to live at one of the two poles, you're going to have 6 months of just plain sunlight with no darkness at all. And then you're going to have 6 months of just plain darkness with no sunlight with no sunlight at all. So the further away you get from the equator, the greater the difference between winter and summer becomes. But one of the reasons why it's so warm near the equator is because the sun is almost always overhead. Meanwhile, the reason why it's so cold near the poles is because when the sun is even out, it's low on the horizon. And as a result, that sunlight that comes in spreads out over a larger area, and therefore it's just not as intense. This actually creates an interesting situation where near the equator, they have an energy surplus. What this means is that near the equator, they actually receive more shortwave radiation than they give off in longwave radiation. In short, the areas near the equator receive more heat than they give off. They make more income than they spend. On the other hand, near the poles, as you move away from the equator, you get into a region where, or you get into a situation, into a region, where they actually receive less sunlight than they give in long-wave radiation. They receive less energy than they give off. This creates an energy deficit. Now, if nothing were to happen, if we were to let those two, that surplus and those deficits, stay where they're at, the area near the equator would get much, much warmer. The area near the poles would get much, much colder. But thank goodness for Mother Nature, because through many different processes, via ocean currents, via storm systems like hurricanes, via other mechanisms, a lot of that surplus heat from the equator ends up being transported closer to the poles. So in essence, the equator pretty much shares what it gets with the poles. And so that helps get rid of its surplus, and that also helps make up the poles' deficits. If it wasn't for this, the equator would be much, much hotter, and the poles would be much, much colder. And so, and this is a good thing, because if you live near the equator, people who live near the equator, seasons usually aren't that bad. Temperatures aren't usually that bad. I mean, they have high 80s, low 90s year round. It would be like 100, 110, 120 if we didn't have this heat transfer happening. All right, third fact. Earth's orbit is not a perfect circle. I don't think anybody gets the reference to the band A Perfect Circle, but Earth's orbit is not a perfect circle. For some of you, that'll blow your mind, but hear me out. So, Earth's orbit is actually elliptical. I don't know how many of you have come across an ellipse in one of your math classes before, but an ellipse is essentially an oval. It's an oval. That being said, the path that Earth orbits around the sun in is actually a flat path. It is a planar path. What that means is the Earth essentially orbits the sun on a plane, meaning as it's orbiting the sun, it doesn't go up, it doesn't go down, it just revolves around the sun on a flat plane. And we call that plane the plane of the ecliptic. So that is what is referred to as the plane of the ecliptic. That being said, because of the fact that Earth's orbit is actually elliptical, there is a time of the year where Earth is closer to the sun and a time of the year where Earth is farther from the sun. That being said, that is not what causes our seasons. That is not what causes our seasons. There are two reasons why. Reason number one, Earth's actual orbit around the sun is not a perfect circle, but it's pretty damn close. What I mean by that is that Earth's orbit around the sun is almost a circle. It's only slightly elliptical. So during the time that we're closer to the sun, we're only a little bit closer. During the time we're farther from the sun, we're only a little bit farther. Does that have an impact? Yes, but not a very big one. Here's the second thing. The second thing is that if it was the distance from the sun that actually dictated our seasons, both hemispheres would have the same season year-round. What I mean by that is that if we are in summer, our friends in South America are also in summer. If we are in winter, our friends in Australia are in winter. But that's not true. Believe it or not, the seasons flip. Summer here is winter in Australia. Winter here is summer in Australia. And then one last interesting piece of information. If it was the distance from the sun that actually dictated our seasons, our warmest time of year would not be July, August, or June, July, and August. Our warmest time of year would actually be in January. Here's why. We are closest to the sun in January. We are closest to the sun in January. There's actually a day for this. The day is what is called perihelion. Let me actually underline the whole thing. And perihelion occurs roughly between January 2nd and 5th. It is on that day that we are closest to the sun. On the other hand, we are farthest from the sun on a day called aphelion, and that actually takes place between July 3rd and 6th. So you've already lost your opportunity to do this year, but next year, when the 4th of July approaches, run around your neighborhood holding up sparklers and yell, "Happy aphelion, everybody!" And they'll all look at you, point, and laugh. But that being said, we're actually farthest from the sun in July. So nope, so the distance from the sun is not really what dictates our seasons. Is there some difference caused by it? Absolutely. For us here in the Northern Hemisphere, our winters are very slightly warmer and our summers are very slightly cooler. But that's really it. And then in the Southern Hemisphere, their summers are very slightly warmer and their winters are very slightly cooler. So we'll go over that again real quick. Earth is closest to the sun in January. Earth is farther from the sun in July. So what does cause our seasons? What does cause our seasons? Well, it's all about axial tilt. Tilt is the reason for the seasons. Tilt is the reason for the seasons. So here's what I mean by tilt. So if you actually thought about the Earth as a giant globe and you stuck a long stick in the middle of it, that stick is what would be called its axis of rotation. As the Earth rotates, that stick is the center of the rotation. Now, what's interesting is that relative to Earth's plane, that flat surface that the Earth orbits the sun on, Earth's axis does not stand straight up. Instead, it is tilted at an angle of about 23.5 degrees. So Earth's axis is tilted at about 23.5 degrees. That is what gives us our seasons. It is the tilt that gives us our seasons. So the axis does not point straight up. Instead, it's tilted. And it's tilted at an angle of 23.5 degrees. One interesting thing about this is the angle of Earth's tilt actually does change. It actually changes in a process called obliquity that takes about 40,000 years. But the difference between high angle and low angle, or low angle and high angle, is roughly 2.5 degrees. So Earth's axis does change, but it doesn't change by much. All right, so what is the consequence of this? Well, I wish I had my globe with me. I left my globe back on campus back in the good old days. But if I were to actually use this drawing pad again, I already used this drawing pad again, and let's assume that this is like the Earth's axis, in a sense. Well, not so much the Earth's axis, but this just represents, well, actually, yeah, I'll say it like that. This represents the Earth's axis. Well, what actually happens is, in the summertime, the North Pole is tilted towards the sun. During that time, the Northern Hemisphere receives more sunlight than the Southern Hemisphere. If you notice, the top of my board is tilted towards my flashlight, and therefore the top of my board is receiving, sorry it keeps fading out, it's receiving more sun. Well, as we actually go into wintertime, the southern pole, the South Pole, is tilted towards the sun, and the south receives more sunlight. than the North does. And that is why that tilt causes seasons. Because as the Earth revolves around the sun, where the axis itself is pointed at does not change. But what does change is when the Earth is over Nya, the southern pole, the South Pole, is pointing towards the sun. And so the southern hemisphere gets more sunlight. Meanwhile, over Nya, the northern hemisphere gets more sunlight because the North Pole is pointing towards the sun. Meanwhile, in September and March, we just passed the September one about a week and a half ago. In September and March, that tilt, the axis tilt, is not pointing either towards or away from the sun. It is perpendicular to the sun. In that case, both hemispheres receive the same amount of sunlight, and that is what is referred to as an equinox. All right. So, fact number 5, seasons flip when you cross the equator. So yes, right now, as our leaves are starting to change color, as we're grabbing our pumpkin spice lattes and putting on warmer weather clothes, not today, the highest forecast for 97, but as we do that, our friends in the southern hemisphere are actually starting to put away their cold weather clothes, and they're starting to go out more. They're starting to, well, kind of a weird year for that, but still, they're starting to picnic more. They're starting to barbecue more. They're starting to do more outdoor activities because the weather conditions are warming down there. So as we're starting to cool down, hopefully, they're starting to warm up. So because of Earth's tilt, one hemisphere gets more sunlight than the other. In the months of March through September, that's us in the northern hemisphere. We get more sunlight. Our spring is March through June. Our summer is June through September. Our fall is September to December. And our winter is December to March. On the other hand, in the southern hemisphere, they actually get most of their sunlight in that period from September to March. So September, October, November, December, January, February. That is when the southern hemisphere gets most of its sunlight. So their spring has just started, and it continues until September. Their summertime starts in December and goes to March. Their fall starts in March and goes to June. And their winter goes from June to September. So yes, as Santa Claus is making his way down to Australia, South Africa, and South America, well, Southern Africa and South America, he has to change his wardrobe because that very, very thick coat isn't going to cut it down there. It's way too hot. And yes, while we are inside with a roaring fire, snuggled up with a cup of hot cocoa, and trying to keep ourselves warm on Christmas Day, in the Southern Hemisphere, they're out barbecuing, they're hitting the beach. It's almost like the 4th of July for them because that is like their summer holiday. Kind of blows your mind to think of that. But and this image right here sort of shows the exactly how Earth's tilt does influence which hemisphere gets more incoming sunlight. In the spring and summer months, red right here represents the equator. In the spring and summer months, the northern hemisphere, our spring and summer months, I'm sorry. So this is March. Let me write it down. This is March to September. During that March to September time, the northern hemisphere is getting the bulk of incoming sunlight, and as a result, it's much hotter. Whereas the southern hemisphere is only getting a little wedge of sunlight, so it's colder for them. Then 6 months later, the Earth makes half of its orbit around the sun. So it was here, now it's here. And the setup looks like this. In this case, the southern hemisphere is getting the bulk of incoming sunlight, and the northern hemisphere gets less. So there are a few important days to remember. So in general, I tell people that dates are only important on Friday and Saturday night. That being said, there are a couple of important days that are worth remembering. Here in the Northern Hemisphere, the 4 big dates that we need to remember are the summer solstice, which occurs between June 21st and June 22nd. On that day, the overhead position of the sun, so the latitude where the sun is directly overhead, is at its farthest north. It's on this day that the sun is directly overhead at 23.5 degrees north. And that latitude is what we refer to as the Tropic of Cancer. Meanwhile, 6 months later, when you get into December 21st to December 22nd, as we're quickly approaching that, that is when the sun is directly overhead at 23.5 degrees south. That's when essentially the sun, the overhead position of the sun is the farthest from the northern hemisphere. And in that case, that latitude, what we refer to as the Tropic of Capricorn, gets the most direct sunlight. So our summer solstice is June 21st or 22nd. It depends on what time zone you live in. It varies slightly from year to year. Our winter solstice is December 21st or 22nd. During our summer solstice, the sun is directly overhead at 23.5 north. During the winter solstice, it's directly overhead at 23.5 south. The other 2 days that are important to remember are what are called the equinoxes. It's on the equinoxes that the sun is directly over the equator. On that day, both the northern and southern hemispheres get the exact same amount of sunlight, and they have the exact same length day, 12 hours long. And here in the northern hemisphere, the spring equinox, also often referred to as the vernal equinox, takes place on March 21st or 22nd, once again, depending on what time zone you live in. And the autumnal equinox, that's when the sun is heading back to the southern hemisphere, that takes place on September 22nd or 23rd. And it's on these 2 days that both hemispheres receive the same amount of sunlight. It's on these 2 days that both hemispheres receive the same amount of sunlight. So just to recap, and I can even type this in chat to sort of help keep a record of it, but just to recap, summer solstice is on June 21st or 22nd. Winter solstice is on December 21st or 22nd. And then the spring equinox is on March 21st or 22nd. And finally, the autumnal equinox is on September 22nd or 23rd. just to help keep track of those dates. Now, if I ask a question like this on a quiz or on a test or on a whatever, I'm not going to make you pick June 19th, June 20th, June 21st. I just want you to know summer solstice is in late June. Winter solstice, late December. Spring equinox, late March. Autumnal equinox, late September. That's what I really want you to get from that. Just know approximately what time of year those things happen. And this actually shows how the incoming sunlight looks like during those particular days. So on March, if you notice, both hemispheres getting the same amount of sunlight. Same is true for September. In June, if I were to draw the equator, I didn't draw it that well, but the point still stands that the northern hemisphere gets more than the southern hemisphere. And then in December, see if I could draw this better. That's okay. One more time. The point is that in December, it's the southern hemisphere that gets the bulk of incoming sunlight. Now, here's one other crazy thing to think about. So, Earth's axis of rotation, if I were to draw Earth's axis of rotation, it would look something like this. And then Earth revolves like that. Earth rotates like that. Well, if you notice, the northern pole here in June, regardless of the Earth's rotation, the North Pole actually is always in sunlight. So if you live near the North Pole in the summertime, guess what? The sun's not coming down. Good luck trying to sleep in that kind of environment. I cannot imagine how that must feel like. Meanwhile, for our friends who live at the South Pole Station in Antarctica, there is actually a station at the South Pole. During that time of year, sun never comes up. Even as the Earth is rotating, the sun never comes up there. So it's just never-ending darkness. Now, the cool thing is they get lots of aurora borealis, so that's kind of cool. Well, in the southern hemisphere, it's called aurora australis. But just an interesting thing. So not only do seasons affect the angle of incoming sunlight and which hemisphere is getting more sunlight, but they also affect the length of the day. Seasons also affect the length of the day. And I think that's pretty common sense. I mean, think about the last few weeks or the last month or two. 2 months ago, the sun wasn't setting until 8:30. Now the sun is down by 7. Within the next few weeks, it'll be down by like 6:30. Then we set our clocks back. And well, that's because as we are transitioning into fall and winter, our day length is getting shorter and shorter and shorter. Our days are becoming shorter and our nights are becoming longer. But an interesting fact is that this difference from day to night is very, very tiny near the equator and very, very great near the poles. So that being said, the amount of incoming sunlight that you get, the amount of insolation, the incoming shortwave radiation, varies throughout the year. This affects how long the day is. It's longer in the summer, shorter in the winter. And, of course, the angle of incoming sunlight. Higher in the summer, lower in the winter. So here's a location right here. And these two arcs, these two dotted paths, are the path of the sun on a particular day. In June, the path of the sun is much longer. As a result, the day is much longer. And because the path is higher, the sun is higher in the sky. Meanwhile, in December, the path is a lot shorter, so the day is a lot shorter, and the sun is lower in the sky. So seasons affect both of these things: how much sunlight you get and how long the sun is out for. So that being said, I keep on saying an interesting fact. I find this all interesting. I apologize for how much I'm geeking out. But what's really fascinating about this is that the difference in length of day from winter to summer changes pretty substantially with your latitude. If you live on the equator, 12-hour days year-round. The further away you get from the equator, the bigger the difference is from winter to summer. So if you're a little bit north of the equator, such as this green line, which represents 35 degrees north, that's just south of where we live, they get 14-ish hour days in the summertime and 9-ish hour days in the wintertime. If you move further north, such as 50 degrees north, now you're talking like Seattle, Washington, Chicago, Illinois, places like that. What you're getting on days like that, actually Chicago's not that far north, but still, if you live on 50 degrees north or near 50 degrees north, you only get a 7-hour day in the wintertime, and you get a 17-hour day in the summertime. So a big difference from winter to summer. Then if you live at 66.5 degrees north, this is what is called the Arctic Circle. Anywhere north of the Arctic Circle, you have at least one 24-hour day where the sun's out all 24 hours and at least one 24-hour night where the sun is down for all the 24 hours. So that's a big difference from winter to summer. And then finally, the crazy thing is, if you live on the pole, you get 6 straight months of daylight and 6 straight months of night. So literally on September 21st, the sun set at the North Pole, and it won't come back up again until March 21st. I hope they enjoyed that sunset, because they're not going to get another one for another 6 months, actually for another year. But yeah, just imagine trying to be productive living in an area like that, where you have 24-hour days in the summer and 24-hour nights in the winter. I couldn't do it. I don't know how Santa's done it. Obviously, I'm joking there. Okay, how does this actually relate to climate change? This is a climate change class. It is important that we actually talk about the impact that this has on climate change. Well, these seasonal variations actually split Earth up into 3 main climate zones. The 3 main climate zones are called tropical, temperate, and polar. A tropical climate zone, this is the region between the equator and 23.5 degrees from the equator. Tropical climate zones get consistent sunlight, and a lot of it. So they tend to be warm year-round. In fact, I have friends who are missionaries in Nicaragua, and I was talking to them a few weeks ago about seasons, and they had told me that it's their winter right now. What's interesting is that Nicaragua is actually north of the equator. So geographically speaking, astronomically speaking, their summer is our summer. But culturally speaking, and that is just as important, culturally speaking, because their temperature doesn't really change year-round, they define their seasons more on precipitation. And they get the bulk of their precipitation in June, July, and August, whereas December, January, and February are pretty dry. So they consider June, July, and August to be sort of their winter season, and what we would normally consider our summer season, and then they consider like December to be their summer season. And that is all because they live close to the equator. They get lots of sunlight year round. They have very little change in actual incoming sunlight or temperature. What changes for them is their precipitation pattern. And we'll talk about that in the future. But very little change in day length or angle of insolation, angle of incoming sunlight. Moving away from there, we get into the temperate region of the Earth. This is where we live. This is between 23.5 and 66.5. We live approximately 36 degrees north, maybe closer to 37. Oops, let me close that parentheses. We live right around 36 degrees north. Here, we get lots of sunlight in the summertime. Lots of sunlight in the summertime. And we get 14, 15, 16-hour days in the summertime. Meanwhile, in the wintertime, we definitely get a noticeably less amount of sunlight and a noticeably shorter day length. In the wintertime, the sun will come out 6:30, 7 o'clock. It sets by 4 o'clock, 4:30, usually dark by 5. Well, that's a moderate change in day length, and it's a moderate change in where the sun is located. When you're in June and July, the sun is very high in the sky. When you're in December and January, the sun is typically pretty low on the horizon. And then finally, the third climate zone is the polar climate zone. The polar climate zone has plenty of sunlight in the summertime because the sun is always out, but it's coming in at a low angle. And then little, if any, sunlight in the winter. If the sun is out, it's only out briefly, and it's only at a very, very low angle. So it's very, very dim. And so they get a really extreme change, not just in day length, but also in the amount of sunlight they receive. So even when the sun is out, it's low on the horizon. So this actually leads to some pretty interesting consequences that do have major impacts on our climate. If you live near the equator, temperatures don't really change much from winter to summer. The further away you get from the equator, the bigger the temperature difference becomes. And this is actually what fuels a lot of our weather. You ever wonder why we don't get rain here in the summertime in California? Believe it or not, it's these temperature differences that play the biggest part. It's these temperature differences that play the biggest part. So, tropical zone, plenty of sunlight year round. Temperate zone, pretty good variation. Lots of sunlight in the summer, a bit less in the winter. Polar zone, extreme variation. Very little sunlight in the winter, some sunlight, but at a low angle in the summertime. And how does climate change impact this? Well, as the Earth continues to warm, that imbalance that occurs between the equator and the poles is also going to change. One of the ways, or one of the main hypotheses, maybe I should say theory, there actually is a lot of evidence to back this up. one of the prevailing theories right now about how climate change is going to affect these climate zones is if you live near the equator, you're not going to see a big change in temperature. Areas near the equator aren't really warming up a whole lot. However, if you live near the poles, both the North Pole and the South Pole, are seeing the biggest amount of warming. And this is actually being seen now almost every single year, even in the wintertime. Areas in Greenland, areas in central and northern Alaska, northern Canada, Siberia, the Nordic countries, so like Finland, Estonia, Latvia, Lithuania, many of these northern areas have actually not been getting as cold in the wintertime. They've not been getting as cold in the wintertime. What's scary about this is that difference between warmth at the equator and cold at the pole is what fuels our weather. Well, as the Earth is warming up, as I just mentioned, the equator is not really seeing a lot of change, but the poles are warming up quite a bit. That makes that difference between the equator and the pole a lot smaller. That actually slows down our weather. We get less storms, they're not as intense. And that may sound like a good thing. We don't want intense storms. So that may sound like a good thing. But if you live in California, a place that gets all of its rain on those winter storms, and now we're not getting as many winter storms, that potentially causes drought here. So that imbalance between hot equator and cold pole is being thrown off by climate change. It's being thrown off by climate change. Let me illustrate this just a little bit more, just for a few more minutes, and then we'll be done today. So, here are the temperatures near the equator in January. And here are the temperatures up here near the pole, the North Pole in January. The difference from the equator, which has temperatures in the 80s, to the coldest temperatures near the pole, which in northern Siberia drop below -50, that is a 130-degree temperature difference. Meanwhile, in the southern hemisphere, the difference between 80s, some 90s, and 30s, that's only a 60-degree temperature difference. So the wintertime hemisphere has a big difference. Meanwhile, the hemisphere that's experiencing summer has a small difference. This usually makes winter weather more stormy and summer weather more dry. Now watch what happens, and just for the sake of really illustrating how extreme this can be, take a look at this area right here. I'm going to place an X right here, the coldest region in northern Siberia. Watch what happens when I transition from January to July. Oops. Boom. Look at how the equator changes. January, the equator's in the 80s. July, the equator's in the 80s. Meanwhile, that area in Siberia that was below -50 in the wintertime is now above +50 in the wintertime. Well, the scary thing is, as our climate is changing, this difference between the equator and the pole actually is becoming smaller. It's actually becoming smaller. And as that happens, our whole weather system is disrupted. So that's one of the reasons why seasons are important, and that's one of the reasons why we are concerned so much about how climate change is affecting individual locations. Because if we change these differences, that changes everything. And as we're adding more heat into our system, that changes these differences. Last thing I'll say, happy holidays from Australia. While we are building snow people, and as we're building snow people and we're trying to stay warm here in North America, down there, they are surfing, they are at the beach, they are barbecuing, they're building sand people instead of snow people. All right, so that's it for today. Let me mention a few announcements real quick. So number one, our second quiz is now open. If you haven't seen the study guide yet, it's on Canvas. So if you go to our Canvas page, you click on study guide, or go to our Canvas homepage, go down to quiz study guides. It's study guide number 2. And it covers and the quiz covers everything up until Tuesday. So it doesn't cover today's stuff. And it's open now, and you have until 11:59 p.m. on Sunday night to do it. Yeah, you have until 11:59 p.m. on Sunday night to do it. So it's open now, you have until Sunday night to do it. The other announcement I'll make is, we don't have to think about this right now, but the dirty M word is coming up soon. Midterm. In this next week, I'll get a study guide together for that. We will do a full review session for it. It is comprehensive up until pretty much right before the midterm. I will get a study guide together for it though. And let's see here what our questions are. What lessons is this quiz on? So this quiz is on lessons 4 through 8. And this was lesson 10 today. So lessons 4 through 8. And the midterm will be 2 weeks from today. And it'll work just like one of the quizzes. It'll open up just at about the same time that we dismiss. And you'll have until the end of the weekend to do it. Yes, it'll be formatted almost the exact same way, just longer. So instead of 10 multiple choice questions, it'll have 35. And instead of 1 written question, it'll have 4. There is no lockdown browser, so I'm not going to make you do that. I will make you cite anything that you do use. And it will be timed. That's one thing that's different from the quizzes, is that it will be timed. You'll have 90 minutes. All right. Any other questions I can answer right now? Just wanted to give a moment in case anybody was still typing something into chat. All right, well, that's everything for today. Have an awesome day, everybody. I will see you all on Tuesday. And thank you so much for a great class. See you all on Tuesday. Bye.
Thank you. See you.
Have a great weekend, everybody. It should cool down. I can hang out for a moment if anybody has any questions. Otherwise, I'm going to sign off in a minute. And if you have questions, please don't hesitate to send me an email. Alrighty, I'm going to sign off. Have a great weekend.